reaction, and we are talking about elimination of 2R, 3S, 2-bromine, 3-methyl pentane. Which we said, if I really am not good, again I repeat, if I'm not good, with 3D, the safest way will be going from Fischer to Newman. And I will remind you, or I will tell you in case it has not been taught. When it comes to Fischer projection, generally the longest carbon chain is the backbone, and then the groups are the ribs. So this is Fischer rule. Of course it's 2D, not 3D. But that being said, I said if I am using Fischer for the purpose of assigning R and S, I am on the riding seat, I do whatever I like to. As long as I'm correct. I said, according to Fischer, groups that they are on vertical, they are in the back. Groups that they are on horizontal, I call them hugging groups. They are coming towards you. So with that, if I have my group with least priority on vertical line, it's very easy to write R and S, which you can see hydrogen is in the back, just assign priority A, B, C, R. Hydrogen is in the back, assign priority A, B, C, R, which it tells me right now I am not using the correct structure. Agree, guys? Because we said 2S. So to be correct, what should I do? And it's not that I am not aware. I am trying to explain Fischer and its application. Okay. Now, again, I will remind you Fischer, vertical line, or ribs. They are eclipsed. So when we go to Newman projection, we only have, obviously, the least stable conformance, because all groups are eclipsed. And I said that the way that we draw the Newman projection from Fischer depends on whether you are looking down the axis from top to bottom or bottom to top. It won't make any difference in your stereochemistry, guys. If you are looking from top to bottom, the front carbon is the top carbon. If you are looking from bottom to top, obviously the lower carbon is going to be the front carbon. That's all there is to it. So in this case, I'm going to go carbon number 2, carbon number 3. Okay, so this is direct conversion of Fischer to Newman, or vice versa, by the way. You know, you can do both ways. Why you want to do it both ways? Because there are times that you have a Newman projection and you are not sure about your stereochemistry. You can do the same principle, assign R and S, because Fischer is the easiest projection, guys, for assigning R and S, I have to tell you, of course. 3D came way, way after. Fisher, and I have to confess, during my generation there were not such a thing as wedge and dash. It was either Fisher or Sawhorse. There was not even Newman. Newman, wedge and dash, they all came later. That tells you how many centuries I have been around. So, that being said, now, you and I know that the two departing groups should be
180 degrees.
180 degrees apart on Newman projection or 3D Sawhorse. You know, our version of 3D was Sawhorse, by the way. So Sawhorse was the 3D configurations that we are using now. So in either case, they are staggered, not eclipsed. Now, one thing that we know, with sp3 hybridized carbon, we have free carbon-carbon bond rotation. So I want this group that is going to depart, and this hydrogen, don't forget, it takes two carbons. One carbon has the leaving group, the other carbon has the hydrogen. So you want daily 180 degrees. So all I have to do, I have to make 60 degree rotation on page. That's right. So making 60 degree rotation, I have to tell you, for make it easy for myself, when I am making conformers of Newman projection, I always keep one group as is. Even though I know it's free rotation, so both of them are rotating around, I have that freedom. That to make it easy for myself, I keep one group as is. And as you guessed, I have decided to keep the front carbon as is and rotate the back carbon so hydrogen, ethyl, and metal. So this is the conformer that will undergo elimination. So now that I have the right conformer, I will pay attention to see what will happen to our stereochemistry. So base will come and take this proton away. That would be the driving force to move your leading group. One thing that you know in organic chemistry, when it comes to chemical reactions, those kind of things, we do not write balance equation. The only thing that we count for every atom, every electron is mechanism gas. So now we know we are getting carbon-carbon double bond. Now the question is it E or C? First we have to decide which carbon is carbon number 2, which carbon is number 3, guys. It's pretty contrary, I'm taking both. Which carbon do you want to be? The left carbon, 2 or 3? Okay, so carbon number 2, we decided to be carbon that is on the left side. So I am looking at carbon number 2. Remember, carbon number 2 is front carbon. It was bonded to bromide, which is gone, CH3H. So I'm going to randomly write those two groups. Okay. Now, and I'm going to write it even though you know one means metal group. Now, there is something that stereochemistry is important. Carbon 2, carbon 3. What is the relationship between the two group, guys? Are they opposite or the same side? Look at these two. Look at these two. What is their stereo relationship? Are they opposite or same side?
Opposite.
Are these two opposite? Are they both coming towards me as I am looking here? Or as you are looking on your page? On these two groups, the same direction. Guys, okay, I'm not going to put this because you think polar. Opposite, doesn't opposite mean?
No.
Okay? Guys, get your directions. Okay, I don't say anymore. So, you and I see methyl group on carbon number 2 and ethyl group on carbon number 3 are same side. Because that's something that is important. Also, we see methyl group on carbon number 3 and hydrogen on carbon number 2 are same side. So that's what we do. Okay? This is the correct stereochemistry. Not that I have correct stereochemistry, I assign EZ. Is this E or Z? What do you think, guys? Definitely C. Okay, now, one thing that I have to tell you, a pair of enantiomers form the same diastereomer. I repeat what I said, and I will ask you what is your conclusion. A pair of enantiomers produce the same diastereomer. Was my diastereomer plural? I said diastereomer, didn't I? It means only one. So what it means this will be product, E2 product of either 2R 3S or 2S 3R. Guys, two bromo, 3 methyl, pentane. Okay. Enantiomers of haloalkane produce the same alkene. That's the nice thing about it. So we do not have to isolate enantiomers. Because if you remember your CHE118A, to make haloalkane, you would do free radical halogenation. When you were doing free radical halogenation, you will get a pair of enantiomer, not a pure enantiomer. So, when it comes, if I want my haloalkane for E2, it doesn't have to be pure enantiomer. I can use either of the two enantiomers and get the same product. Now, on the other hand, if I was using 2S, 3S, would I get the same diastereomer? Absolutely not. I would get
You would get the other diastereomer,
which is
which would be the E, right?
absolutely. So if I use diastereomer, I will get diastereomers. Okay, guys? Using diastereomers, you end up with diastereomers. Using enantiomer, you will end up with one diastereomer of alkene, not two. So these are as far as E2 reaction. The next reaction that we can make alkene, and you have learned, is dehydration of alcohols. Now, when it comes to dehydration of alcohols, I will bring to your attention, I have written, it can be E1 or E2. E1, to the best of my knowledge, is not being applied in research, organic life. Industry uses E1. Sorry, E2. Industry uses E2. We do not. In organic lab research, we do not use E2 reaction for dehydration of alcohol. Why is that? Let's go back. Guys, are you done? And I truly am sorry for not having extra chalkboard. You know, anytime I'm walking, I feel guilty. I said, what have I done with that? I denied myself from extra chalkboard.
Professor?
Yes.
Anti-Perry planar. I couldn't find. I've seen it. It's exactly that, but I couldn't find it in the index glossary. Whatever. Anti-Perry planar.
I guess they have to. There has to be a reason they pay us. I'm serious. You know, there are certain things. Each of us will make contribution that you will not see in your textbook. We read several textbooks, and we take the best and share with you. Yes?
I think they refer to it as anti-coplanar in the textbook. That's probably why you're not being able to find.
Well, there's another one that says anti-Perry planar. I couldn't even remember which chapter it's in, but I think they're referring to the exact same position.
That's what I am using. That's what her way of telling you. Textbook says coplanar.
Yeah.
Yes? Textbook says coplanar.
Okay.
But when it comes to coplanar, again, it could be syn anti. And they don't, say periplanar. They say coplanar. You know.
Thank you.
But to be honest, when I am looking at textbooks, I do not pay close attention to certain vocabulary. And it's not that I don't want to. Because to me, they are the same, so I don't realize, hey, I'm using this textbook for this class, the other. But nonetheless, it wouldn't hurt to be familiar with different vocabulary. Don't forget, when you are taking any professional examination, they ask you all types of questions, except two. Which school did you go? Who was your OChem teacher? Okay, guys? And so obviously my job is, as your partner in education, to prepare you to the best of my ability to take anyone's exam, not only mine. So I want you to be familiar. Now we are talking about hydration, and dehydration, sorry. Hydration is going to be maybe in half an hour or so. So going back to chapter 9, you have learned that you can dehydrate alcohols. Now, in the first place, I don't need one more carbon, don't forget. We need 2 racemium carbons to do dehydration. One must have leaving group, one must have hydrogen. Now, when it comes to dehydration of alcohol, it means one carbon is losing OH, the other carbon again is losing H. Now I'm going to ask you, would you consider OH a leaving group? Forget that. A good leaving group, OH is not leaving group. So in order we do dehydration, what should we do, guys? We have to turn it into oxonium ion that leaves as water. Absolutely, because water is okay leaving group. Not only that, again, another thing that I have to tell you is, in order for us to turn it into water, we have to use acid. Now, I don't know if you do remember or not, alcohols in acidic medium, they could do elimination or substitution. So first, we have to be careful about acids. Now, probably I am going to tell you something that is not in any textbook, and I use vocabulary. These are the vocabulary that when I was sitting on similar seats, in order to help myself to know what to do, I had to use certain things that only I knew what am I talking about, and I shared with you. When it comes to acid, I know you classify them in all sorts, strong, weak, mono, di, triprotic, you name it. But in OChem, the only thing that does matter when it comes to classification of acids is, in my vocabulary, for OChem purpose, nucleophilic. Obviously, if I call a nucleophilic, it means what kind of reaction I expect as? Substitution. Okay? If I call it nucleophilic, it means SN, either 1, 4, 2, and non-nucleophilic. Non-nucleophilic means only acid. Only acid means what, guys? Produces a proton. Is that right? You can neutralize a base. You can produce a proton to use it. Now, when it comes to non-nucleophilic, the list is very short. That's why I will give you the short list. Then anything that is not in this short list, HF is one. Of course, AQ or parotic, which alcohols are parotic. In case you have forgotten, remember, alcohols, amines, anytime you have hydrogen bonded either to oxygen or nitrogen, it is parotic compound. So, alcohols are parotic. Sulfuric acid, phosphoric acid. Okay. So when you are hearing these acids, again I repeat, these are the ones that if you do not want to be worried about substitution and you only need proton, you will use them. The sulfuric acid, phosphoric acid are more popular, by the way, than HF. Any idea why HF is not that popular in OChem? I'm asking general chemistry question, I know that. No, that's not, as a matter of fact, it's weak acid. No, HF is not too reactive. Berberine is too reactive. HF is not. Okay, guys, so generally when you are using reactions, you will use flask, don't you? Or test tube. What are they made of? What is the matter, the substance, the compound, I don't want to give its name away, that makes glass? Silicon dioxide. The HF they use for glass etching. So is it a smart idea to have a reaction flask that you are heating it and have HF? Well, you know, yes, it is crazy. Because if you are using Bunsen burner, it will be turned off. Okay? So, that's why commonly you will see that sulfuric acid, phosphoric acid are more popular, guys. And of course, there are times that HF is being used. Now, if HF is being used, do we use glassware? Stay away from glassware in presence of the HF. Okay, so that means that now, the other thing that it is important, you must use heat, guys. You must use heat. And when it comes heat, there are only one time that I will ask the student to memorize numbers. And the only time that I ask them to memorize numbers is when we are using alcohols. Why is that? Because if you do the reaction at one temperature, you will get alkene. Same thing if you do it at 140 degrees, guess what you get? Chapter 9. Ether. Okay. Obviously, you have seen the mechanism. I'm not going to go over the mechanism for this one. I only will tell you, obviously, this elimination primary you can never ever have SN1 or E1. So if it is elimination is E2, if it is substitution, it's going to be SN2. And they only depend on temperature, not type of acid. But secondary, tertiary, it is common to prepare alkenes from secondary and tertiary. So I'm going to now write the one that we will talk about mechanism.
Professor?
Yes, sir.
All SN1 reactions are carbocation mechanisms. Same with E1, or are there some
Yes.
of them? They're all
Absolutely.
all carbocation.
Because
every single one.
SN1 and E1 go parallel. It's just a matter of which one is more favorable than the other. With alcohol, only temperature determines, not time, guys. Only temperature. Now, when it comes to secondary, no problem. We can use any acid because I already used phosphoric. Sulfuric this time I am going to use phosphoric. Now notice the temperature. And of course, I have rounded off them, and I'm going to tell you why I have rounded them off. When I'm teaching 118A, generally during the fall, I will teach one section of Chem 118A. So I will tell the students to remember two numbers. The two numbers that I ask them to remember is 180, which it is the highest temperature for elimination, and 40 degree interval, which it means as you go from primary to secondary for elimination, you reduce it by 40 degrees. Going from secondary to tertiary, what are you going to do, guys? Again, you are going to reduce it by 40 degrees. So I want you to know, this is commonly reduced. That between you and I, all being said, on exam, if you just see the symbol of heat, because we are talking about elimination reactions, we are not talking about ES guys. Keep in mind, I want you to know, I don't mean you make ether as major organic product, regardless of temperature. Because nonetheless, I am giving you a hint, I want you to be aware of it, because probably when they were giving you the mechanism of reactions of alcohol, you were wondering why one time I get ether, the other time I get carbon-carbon double bond. And so I am clearing that part, that between you and I, we are talking about the chemistry of alkenes. Ethers are gone. In OCHEM, the only use of ether for us is solvent. So for that, we don't make them. We are talking about alkene, so even if you don't see temperature, assume major organic product. If it is non-nucleophilic acid, your major organic product must be alkene. Exactly. So here we would expect to be carbon-carbon double bond. Now I want to tell you first, if you have secondary or tertiary, it means E1 mechanism. Okay. And the other thing that I want you to know, when it comes to product, if you have heat, do you want more stable or less stable compound? More stable. So when it comes to dehydration, there is not such a thing as Hoffman as major organic product. It is always the most stable alkene. And by saying the most stable alkene, of course I mean the most substituted, and if there is a choice between cis or trans, then it would be trans. So keep in mind, guys, because here we do not have a stereochemistry problem. They do not have a steric hindrance. So alkene products of E1 reactions are always the most stable alkenes. So keep that in mind. Now I will give you one other. Then we will talk about mechanism. Okay, I'm going to ask you to write major organic product of this reaction. It's obvious. Am I correct, guys? You expect more substituted alkene. Of course, it's 6-member ring, so you don't have to be worried about the stereochemistry. But definitely you want more substituted. Now let's look at the mechanism. And I will remind you, mechanisms are the one that I said we have to count for every evo, for every electrons, for every atoms. So, And of course, I am writing mechanism for the second one, as you can guess. So what would be the first step of the mechanism? A reaction that anytime you have acid, you should expect. Acid-base reaction, guys. You and I cannot avoid acid-base reaction. The other thing now we have to be careful, reversibility. Now, I have been around atoms, molecules, those kind of things. I want to ask you a question. Has any of you have seen Dr. Dolittle movie? Okay, what is his talent?
He talks to animals, right?
Absolutely. He talks to animals. He can hear animals as well. So pretty much is very much familiar with animals. Now, I have been around atoms and molecules. I understand them, I know them, so I feel comfortable that give nicknames to some of them. And when it comes to oxygen, I do call oxygen a crybaby. Why oxygen is crybaby? Well, oxygen, and you will see in the future, nitrogen is similar, but not exactly as oxygen. Oxygen has lone pair electrons. So anytime see a group that is electron deficient, goes like a child, gives them a big nice smile, offers its lone pair electron. Now, a baby comes to you, offer his toy, his cookie, whatever. You accept it. What that baby will do if you walk with that, or if you eat a cookie. They cry, they want it back. Is that right? Oxygen is similar. Offers its lone pair electron. As soon as it becomes positive, all of a sudden it feels that its pride is hurt. And this is the second most electron-negative atom in periodic table, and now it's positive. You and I know oxygen doesn't want to be positive. Then wants its electron back. Now, when it wants its electron back, that's why we are writing reversible, guys. Because it says, I want my electron back, it takes it from hydrogen, go back. Or, it can do something else. What else it can do? Again, please pay attention. Reversible. So either can go back or can take the electrons away from the vicinal atom. Either case would be vicinal atom, either hydrogen or carbon. But that being said, you and I are familiar with such a thing as primary or secondary carbocation. Okay. We know primary cation does not have a choice or a chance to form and exist for a few seconds. But secondary and tertiary, they can form. They can stay around for a few seconds. But nonetheless, again, we all know carbocation is electron deficient. It will not stay there forever. So When it comes to carbocation, guys, I'm going to ask you what a carbocation can do. Rearrange. That's the first question that I will ask myself. A carbocation can rearrange. You can go from secondary to secondary. You can go from secondary to tertiary. But by the same token, you can go from tertiary to secondary. But which one is more favorable? Going from secondary to tertiary. So in this case, naturally, I will say yes, it can rearrange, but every step is reversible. Agree, guys? Still, formation of more stable, so they may revolve, but still, a tertiary is a little bit more favorable. So that's the first thing I will ask. Rearrange or not? What is the second? After we got that question out of it, then what are we going to ask? What would be the fate of a carbocation? Either elimination or substitution. Okay, guys? Now, for substitution, we need a nucleophile. Okay? And keep in mind, when it comes to carbocation, it is electron deficient. Beggars cannot be choosers. So, any nucleophile is okay. Water is not the best nucleophile in the universe, but nonetheless, I have a carbocation that needs electron battery. So it could react. If water goes back. That's why we are writing reversible. The other thing, it can undergo elimination. Okay. Now, for elimination, what do we need, guys? What do we need for elimination? You always need blank for elimination. Base. Okay? Now, the question is, what is the base here? And I'm going to tell you, when I am writing key for my TAs, I will write any reasonable base. By any reasonable base, I mean anything that is inside the reaction flask. Not I go and take sodium hydroxide from the shelf. Okay. Remember, only within what we have, within our limitation. So I'm going to ask you guys, if you were considering a reasonable base, what they would be, or what they are. Reasonable base says, what are they? What they would be. H2O is one. Any other? The alcohol itself, because alcohol is similar. Don't forget, alcohols have similar group. Water has OH. It's the oxygen that makes it base. It's amphoteric. Alcohols are also, they have OH. It's the same oxygen or amphoteric. So water, alcohol, what else?
Conjugate base.
Absolutely. Dihydrogen phosphate. Any of these three are reasonable. Now, of all the three, I personally use water. And I will explain why I personally use water. Then obviously, as time goes by, you are going to have less and less alcohol. Agree, guys? Because your alcohol is going to react, it will become alkene. As time goes by, you are going to get more and more water. Now, why not phosphoric acid? Why I don't use phosphoric acid? I'm going to ask you. Let's assume that I am going to use dihydrogen phosphate, conjugate base. Okay, so let's assume that I use that. And it's not wrong assumption, etc. So if I use that, I will get phosphoric acid. Now, I have phosphoric acid, I have water. What would I expect? Dissociation, etc. So that's the reason that I commonly use, I want you guys to know, I commonly use water. That again, as long as you don't use alcohol, as long as you don't use your reactant, because you want to make product from it, either dihydrogen phosphate or water are reasonable. Be careful, every step is reversible. That's why these reactions in organic chemistry, they are not that popular, guys.
Yes. Professor, also, don't you have more collisions with water as the solvent? It's tiny.
No, water was not solvent.
Oh, okay.
Water, dehydration, we did not start with water.
Okay. Thank you.
Sure. No, thank you for asking, because I'm sure it helps students to understand that. No.
So alcohol was the solvent
And the reactant,
okay.
Yes. Now, as you guys mentioned, when it comes to even elimination, there is always a problem. It's carbocation rearrangement. So let's start. This reaction and do chemical reaction. And the question is, what are going to be major organic products? As you may guess, this is a reaction that it is not good idea. Why it's not good idea? As you would expect, this one of my cards. Don't forget, when it comes to even reaction, you will get both dioxide. You do not have any stereo requirement during the elimination process. You have a carbocation sp2 hybridized, no aesthetic hindrance. So you will get E and C. Now, in addition to that, what else would you expect to get? one I have to write the mechanism to understand what is going on. This is the place that I am going to get the power on, which is network group. Because I'm going to get the network group, I have the network group there. Okay, so I will get 3 products, and all 3 are in significant amount. So what is going on here? Let's look at mechanism. Step 1, as we would expect, acid-base reaction. Oh, by the way, you guys don't have, you can start to write, a new structure and do your reaction. I'm just running to save some time, now that I don't have too many charts. Chartboard. And hydrogen sulfate. Please be careful. Mechanisms, you have to write every atom. Mechanisms, you cannot lose anything else. Then, as you would expect, water is going to leave. So obviously, even elimination of this intermediate produces the expected E and C. Okay, guys? So this will produce E and Z. So elimination of this will produce E and C. I'm not going to write that one. You know, you can eliminate the proton. That you have carbocation. Carbocation can do what, guys? Rearrange. So now what will happen? So this time we are going to talk about rearrangement. Again, you have carbocation. What do you expect? Rearrange. And you will agree with me, this time rearrangement is even faster. Well, this time rearrangement is even faster. What type of carbocation this is?
Secondary.
Secondary. If the group that I am trying to move it, I write it, I will go from secondary to tertiary carbocation, which you would expect to be more stable. Please write your water, because when I took it, I didn't write it. Now I am going to have rearrangement. which is going to produce the other product. And this time I am going to write minus H3O. So you will get total of 3 products, a pair of diastereomer and a structure of isomer. So this is the main reason that E1 reactions of alcohols are not popular in organic lab. The only time that we are doing any E1 reaction is when we are not going to be worried about carbon-cation rearrangement guys. If you are not worried about carbon-cation rearrangement, E1 is your choice. But even that, keep in mind, you get a pair of E and Z diastereomer. In E2, you don't have that problem. In E1, because E2 always demands a specific stereochemistry. E1 doesn't. So these are as far as the chemistry of chapter 11. Now we are going to move on to chapter 12, for which we are going to talk about reactions of alkenes. The first reaction of alkenes that last time we talked about is hydrogenation. Last time we learned we can add hydrogen to carbon-carbon double bond. And when we are adding hydrogen, what do I need then? We need the reacting catalyst. And again, I repeat, if you don't remember what we use, at least read to CHE. And just don't write hydrogen. Because if you mix them, nothing happens. Doesn't matter how many centuries they are next to each other, nothing happens. So either palladium carbon or platinum carbon, no problem. So, we can add hydrogen to carbon-carbon double. Now we have learned 2 new vocabularies, and the 2 new vocabularies are regioselectivity and stereoselectivity. Did you consider hydrogenation to be regioselective? Did you expect or did you consider hydrogenation as a regioselective? Basically, my question is, there are 2 hydrogens. Did one of them says, I like this carbon, you go there?
Mm-hmm.
Is that right? So when it comes to hydrogenation, it is not regioselective. You have 2 identical atoms, you have 2 hydrogens, 2 carbons. Each of them gets 1. But the reaction is stereoselective. By stereo, I mean if you are going to generate a stereo center, would it be all 4 states? That's what I'm talking about. So when it comes to these reactions, hydrogenation I'm talking about, they are not regioselective, that they are stereoselective. Now, to understand stereoselectivity, which always applies, by the way, guys. Anytime you are using hydrogenation is stereoselective. Why hydrogenations are stereoselective? First, you see we have to use catalyst. Why we have to use catalyst? Because hydrogen is very light gas, is not very reactive either. So we have to make it to become reactive. Now let's go back to our general chemistry. And I'm going to tell you, I'm going to ask you, if you don't answer, then I will tell you. I'm going to ask you, what kinds of hydrogen bond do we have? And I'm not talking about intermolecular forces. I'm talking about chemical bonds. How many kinds of hydrogen bonds are there? And these are 118A, B, C. I'm sorry, 2A, B, C. For honor, if one can get into it. How many types of hydrogen bonds are there? Well, for sure, the most popular one is covalent. Okay. Most of the bonds between hydrogen and other atoms are covalent bonds. A few are ionic, such as sodium hydride. You know, if you say hydride, your hydrogen is negatively charged, which it means it is bonded to metal or metalloids. Then there is a third one, Chem2C to be more specific. Oh yeah, that was a long time ago. Metallic bond, not covalent, not ionic, metallic. What it means, basically we are using catalyst. Okay, so this is the surface of our catalyst. And hydrogen bind to the surface of catalyst. Probably you know each hydrogen has one electron. That's what they use to make covalent bond. But when they come exposed to transition metals, they are being attracted to transition metals. So basically what transition metals are doing, they are trying to break apart the two hydrogens, similar to free radical. So you have more atomic hydrogen guys than covalent H2. Okay, guys? So this is what transition metals do. So the reaction happens on the surface on the catalyst. And your carbon-carbon double bond is passing. Would you expect, if you have bulky group, would you expect that the molecule be intact, the transition metal, I'm talking about alkane, from more hindered side or less hindered side? Yes. Less hindered side. Yes. That's the reason that when it comes to hydrogenation, you can put the groups, it doesn't matter because this one I have not shown which group is larger, which one is smaller. So the way I will look at it, I know when it comes to my alkene guys, I know that alkenes do not have, when it comes to carbon dioxide, it doesn't have wedge or dash. Only for the purpose of understanding, I will make the assumption that I am looking from one side of carbon guys, because this is the most convenient way of looking at it. This is something that will help you. Again, I repeat, when it comes to carbon-carbon double bond, is flat, 120 degrees. Only for the purpose of understanding the stereochemistry, I assume that I am looking at one side. So the groups that they are facing me, I show them wedge. Group that they are in the other side, dash. That's what it is. So when it comes to hydrogenation, now I'm going to... because now